This is my Calculus 1 course. Today we're going to learn definite integrals and the fundamental theorem of calculus. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class we learned how to find antiderivatives, and we also learned the notation used when someone is asking you to find antiderivatives, and that is the indefinite integral. Today we're going to learn what we call the definite integral as opposed to the indefinite integral. Go ahead and get a screenshot of all these differentiation rules if you don't already have those in your file. You're going to need to look back on those and constantly refresh your mind, because these formulas really are the most important part of this course. So you need to know these formulas first and foremost. Now, before we go into definite integrals and the fundamental theorem of calculus, we're going to do a little review, but we're also going to learn some more challenging problems when it comes to finding or doing problems relating to indefinite integrals. So here we have a problem where we're asked to find the antiderivative of this expression. Remember, if you have this symbol and this symbol enclosing an expression like this, then what it's telling you to do is to find the antiderivative of that expression in the middle. The problem is we don't know how to do that with this expression, so we're stuck. It turns out that there's actually quite a few expressions where we don't really know what the antiderivatives are. You can't just plug in anything into this expression and think that you're going to find the antiderivative. So we have to make sure that we actually can find the antiderivative, and a lot of students would look at this and simply say, well, no, it doesn't look like we can do that. We don't know what to do. But this is actually just a trick. All you have to do is just simplify the expression. Remember, we can divide each term by the denominator. We learned how to do this in my beginning algebra course. If you have the sum of a bunch of terms and you divide by something, then you can divide each of those terms by that something, by that denominator. And you can also call this fraction decomposition. That's just another word for it. So now we're dividing powers. So what do? Well, obviously we just subtract the exponents. So we have 2x to the second power, and we have 9x, and we have 4, because 2 minus 2 is 0, but x to the 0 power is 1. Alright, so let's double check everything. Looks like everything is correct. We still need our dx there. I can't forget my dx. Remember, that's just ornamental. It's not multiplication. So now we can find the antiderivative. Looks like it's going to be 2/3 x to the third power plus 9 over 2 x to the second power minus 4x plus c. So we learned how to find antiderivatives in the previous class. You should be somewhat familiar with that. And if you want to check, all we have to do is just find the derivative of this yellow expression, and if we get the green expression, that means that we did it correctly. So it's a good idea to go back and check and find the derivative of this expression to see if you get the expression here. You always want to double check with these problems, and it looks like we do, so we did that correctly. So again, it's a trick. It doesn't look like we can find the antiderivatives, but we can. We just have to simplify first. So don't be tricked by these types of problems. You'll see these quite a bit in textbooks. Now here we have another situation where it doesn't look like we can really do much, but we're just going to use the same method that we used before to simplify the expression. I'm just going to change that to x to the 1/3 power. And of course we just need to subtract the exponents. I'm also going to change this to x to the 1st power. So 1/3 minus 1 is -2/3. And I'm going to change that to 1 power. So 1 minus 1 is 0, and x to the 0 power is 1, so we're just left with 2. Okay, and now we can find the antiderivative. Now remember, if you find the derivative, you subtract 1 from the exponent. But if you find the antiderivative, you add 1 to the exponent if we're talking about a power expression. So that would be x to the 1/3. 1 plus -2/3 is 1/3. Now, if I find the derivative of this expression, remember, using the power rule, you have to take 1/3 and bring it down and multiply it into something, and that should get you nothing. So 1/3 times what is equal to, well, it's not going to be nothing, it's going to be 1. But 1/3 times what is equal to 1? Well, that's just going to be 3. So that tells us we need a 3 in front. And then we get 2x and then plus c. But we're not allowed to leave our exponents in fraction form in my curriculum. Some teachers will be okay with that, but that expression is just too wild looking to really make much sense in the world outside of mathematics. So we need to change that to something that has more meaning. So let's double check, make sure we did this correctly. Looks like we did. So those were situations where we had to simplify. A lot of students will get tricked by those types of problems. They will just get stuck, but always try to simplify the expression before you give up. So again, if you want to check, just find the derivative of this expression and you should get back to this expression here. And we do. So let's try another one. Here's another example where we can just simplify. We don't know how to find the antiderivative of that. We could do it, but it would take methods that we haven't learned yet in the calculus curriculum. So we don't want to have to do that. So I'm going to change x to the 1 power and 4th root of x to x to the 1/4 power. And I'm just going to use exponent rule number 1. Up here in these two problems we used exponent rule number 2. Now of course I'm talking about my curriculum. The exponent rules might be numbered differently depending on what curriculum you're talking about, but in my curriculum this is exponent rule number 1, where we add the exponents because we're multiplying the powers, and we get x to the 5/4 power. So we have not found the antiderivatives yet. All we've done is just simplified the expression. And so now we're going to find the antiderivative. So remember, you have to add 1 to the exponent, and if you do that we get 9/4. So we know that that's going to be the exponent. But remember, when you find the derivative, you have to take the exponent and bring it down and multiply it into something to get nothing. Well, what is that going to be? Well, 9/4 times what is equal to 1? And obviously the answer is 4/9. And then we say plus c, and that's pretty much it. We're done, except we're not allowed to leave our answer with a fraction exponent. So there you go, that is the answer. So again, it's always good to go back and check, make sure everything makes sense, and it looks like it does. So here's another example where we don't know how to do this, but if we use distribution, we get -2x to the 4th, minus 14x to the third dx, and now we can find the antiderivative. Make no mistake about it, we don't know how to find the antiderivatives of this expression here. We just don't know how to do it. But let's now try to find the antiderivative. We know it's going to be x to the fifth power, because remember, you add 1. But then when we find the derivative, we can go backwards. We're going to have to take that 5, bring it down, and multiply it into something to get -2. We need a -2 here. So solve, and we obviously get -2 fifths. Now, over here, we're going to have x to the fourth power. Again, we have to add 1 to the exponent. And when we go backwards and find the derivative, we're going to have to bring that 4 down in front and multiply it into something so that we get -14. So what is that y value? Well, it's -7/2. And you can confirm that that works by finding the derivative again. Don't forget to add your c value. So find the derivative of that, and you should get this original expression here. And it looks like we do. So just one more example where we need to simplify the expression. Now here's another example. We can't find the antiderivatives of this function here, but why not just use FOIL? First, let's use the definition of raising to the second power. That just means you're multiplying whatever you're raising to the second power, you're multiplying it by itself. Then we can use FOIL, and you can just add the inner terms in your head. You don't have to write this out. But of course, we get F, O, I, and L of FOIL. And add the inner terms, and we get x squared plus 10x plus 25 dx. And the antiderivative is going to be 1/3 x cubed plus 5x squared plus 25x plus c. Again, at this point, you should be fairly well versed when it comes to finding antiderivatives. If you're not sure how we found that set of antiderivatives, you can just pause the video and make sure that you understand why, if you take the derivative of this expression that we got, you'll get back to the original expression. Okay, so this one is pretty much the same thing, just using FOIL, but this is actually even easier because it's not an exponential form. So actually, that should be a 2, not a 1. See, that's why you want to constantly go back and check your work. It's very easy to make a mistake. Okay, so now we are going to find the antiderivative, and looks like we have 2x to the third power minus 13/2x to the second power plus 2x plus c. And that is the family of antiderivatives that we're looking for. Now again, the reason we call it a family is because c can be any number. So there's actually an infinite number of antiderivative functions, such that when we find the derivative of that function, we get back to the original function. Because of c or pi or 1000 or 89.6 or whatever, you find the derivative, that goes away, and you get the original expression. So let's double check, make sure we did that correctly. Everything looks right. So here's another example where students would have a lot of trouble because we don't know how to find the antiderivative of an expression like that. It's kind of a puzzle. But recall that we have two formulas that help us with roots. One formula says that the nth root of a times b is equal to the nth root of a times the nth root of b. The second formula tells us that the nth root of a over b is equal to the nth root of a over the nth root of b. So the bad news is that students don't like roots. They don't like dealing with roots. The good news is there's only two formulas that you have to memorize. So there's really no excuse for you not memorizing these formulas. You should know how to use those, how to work with those. So we're going to use the second formula, obviously, and what is n? Well, n can be anything, but in this case, it's that there is no number there. So what is it? Well, of course, we know that it's 2. We just don't write the 2 because square roots are so common that we don't want to constantly write the index, so we just write nothing, but it means that the index is 2. But of course, any index that's higher than 2, we write it in between these two, in that area there. So we're going to have the square root of x over the square root of 3. Then we're going to factor out 1 over root 3. We don't have to do that, but it just makes it easier for students to see what's going on here. And then we're going to change root x to x to the 1/2 power. And now, in this form, we're ready to find the antiderivative. So again, don't be fooled by these problems. It looks like we can't find the antiderivatives, but we can. So remember, you always add 1, so that's going to give us 3/2. Add 1 to the exponent. And when we go backwards and find the derivative to check our answer, we're going to take this exponent and bring it down and multiply it into something in order to get that. Based on the power rule. So 3/2 times what is equal to 1 over root 3. Well, if you solve that, we get 2 over 3 root 3. And you can confirm that when you find the derivative of that, you get back to the original expression. So again, we're not allowed to leave our answers with fraction exponents. So we change that to the square root of x cubed. Now, a lot of students might say, well, wait a second, we have an irrational denominator here. We're not allowed to keep that there. Throughout the curriculum, it is true that you're going to need to know how to change the form of this fraction so that it's rational, the denominator is rational. So you will need to know how to do that. But does every calculus teacher require you to do that? Not necessarily. I mean, it's not really something that's that big of a deal. So I'm not going to make you rationalize the denominator right now. Okay, so let's go back and check to make sure we have the right answer. Everything looks correct. So here's another example of that. But now we're going to have to use the other formula. Remember, there's two formulas for roots. This formula says that the cube root of something times another thing is equal to the cube root of the first thing in the product times the cube root of the second thing in the product. Again, these are just basic rules that we learned all the way back in my beginning algebra course. Although in my beginning algebra course we only focused on square roots. But in my intermediate algebra course we focused on all types of roots pretty much. So now we're going to change to x to the 1/3 power. And now we're ready to find the antiderivative. Remember, we have to add 1 to the exponent, so that gives us 4/3. And when we go backwards and try to test our answer, we have to use the power rule, bring that 4/3 down, and multiply it into something such that we get this. So 4/3 times what number is equal to the cube root of 5? Well, that's obviously equal to 3 times the cube root of 5 over 4. And don't forget to add your c value. So now we just have to write the final answer without a fraction exponent. Remember, in my curriculum, you're not allowed to leave your answer with fraction exponents. So we have 3 times the cube root of 5 over 4 times the cube root of x to the 4th power plus c. And let me make some more room. So there you go. So let's do one more of these problems before you try one on your own. I know you're kind of anxious to try one on your own, but we're going to get to that. Just one more problem here. Now we have a problem where we can actually simplify a fraction by factoring. There's actually a lot of different types of problems like this. I mean, there's 3 types of factoring. There's difference of 2 squares, there's quadratics, and there's GCF problems. And sometimes you can combine all 3 of those into one problem. But we don't want to complicate things right now. I just want you to see that sometimes you can simply factor, and of course we can see that these 2 expressions cancel out, and we're left with x minus 2, and that's pretty easy. That would just be 1/2 x squared minus 2x plus c. That is the family of antiderivative functions. Okay, so again, there's a lot of functions where we can find the antiderivative, and there's a lot of functions where we can't. So we can't just assume that if we write some random expression here that we can find the antiderivative functions or the family of antiderivatives. But sometimes it doesn't look like that we can, but we just have to simplify, and so it's a trick. So what I want you to do is take a picture. I'm going to give you one more chance to take a picture of these formulas, and you can take a picture of all these problems here, and numbers 1 and 2 are going to help you with number 10 in particular. So go ahead and try number 10, and when you come back we'll do it together. Okay, we're back. Remember, we're not allowed to have negative exponents in our final answers. So go ahead and try number 11, and when you come back we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. So go ahead and try number 12. Remember, you have to simplify before you find the antiderivative. So go ahead and try number 12. When you come back, we'll do it together. All right, we're back. If you got that right, Excellent. All right, go ahead and try number 13. Remember, you have to simplify before finding the antiderivatives. When you come back, we'll do it together. Okay, we're back. So there you go. You want to double check, find the derivative of the expression, make sure you did it correctly. Okay, so you can take a picture of all these problems that we did if you want to help you with number 14. And I'm going to give you one more chance to take a picture of these formulas. So try number 14. Again, we don't know how to find the derivative of this expression. Or excuse me, we don't know how to find the antiderivative of this expression. We can find the derivative. We don't know how to find the antiderivative. So we have to change the form of the expression inside here before we find the antiderivative. So try number 14. When you come back, we'll do it together. All right, we're back. If you got that right, excellent. Okay, try number 15. We don't know how to find the antiderivatives of this expression here, so we have to change the form. Try 15. When you come back, we'll do it together. All right, we're back. So there you go, if you got that right. Excellent. Now, they tend to be kind of tricky for students, so you need to use those purple formulas at the left. Again, we don't know how to find the antiderivative of this expression here, so we have to use these formulas. So try number 16. When you come back, we'll do it together. Okay, we're back. If you got that, perfect. Good job. So in this problem, you're actually going to have to use this formula, and then you're going to have to use this formula. Technically, you could actually just use this formula alone. It just depends on how you want to think about this. So see what you can do. You may do it a different way than I do it, but if you get the right answer, then that's fine, as long as you get the right answer. So try number 17, and when you come back, we'll do it together. Okay, we're back. So we got that right. Excellent. And let's see if we can make a little bit more room here. And I want you to try number 18. And when you come back, we'll do it together. Okay, we're back, and that is the answer. So if you got that right, excellent. So now we're going to do some indefinite integrals where we need trigonometric identities. So at this point in your math education, you're expected to know trigonometric identities. And my tendency is to want to put these in front of you, to put the trigonometric identities in front of you so that you can see, where they're coming from. And so I'm tempted to do that. But I really need to stop doing that at this point for you, because you need to learn that, you need to have the confidence to find these formulas yourself. You can go on the internet. If you can't find them on the internet for some reason, they're in my trigonometry course. You can go to my trigonometry course and find the class, and you can find the formulas there. But you're expected to know these formulas and be comfortable with them. Even now, if you're a little rusty on these formulas, or if you don't even remember the formulas, that's actually normal. But at this point in your math education, you're actually expected to remember these formulas, even though most students don't. I want you to start to understand that your calculus teacher is not going to give you these formulas for you necessarily. They're going to expect that you just know these. And I know what you're going to say. You're going to say, well, that's not fair. You know, how do we know that we're supposed to know this stuff? Well, actually, you're expected to know everything from previous math courses. It's not fair that you should recall all of that information, but that's what you're going to be expected to do. So I don't expect you to remember the formulas that we're about to use, but when it comes to you putting in the effort to remember those formulas and actually find the formulas, that's up to you. So you need the basic formulas, the Pythagorean identities, the reciprocal identities, the ratio identities, and even the double angle identities, and even a few more if you want to. So what I'm going to do is I'm going to do the exact thing that I told you just now that I'm not going to do, and that is I'm going to give you all the trigonometric formulas. Most of these you don't have to memorize, but a good portion of them you do have to memorize. And the reason you don't have to memorize all of them is because you don't really use all of them that frequently, but there are a few here that you're going to need to just have them memorized, and if you don't, then you're going to be in big trouble if you take a test or something and you see a situation where you need to have these. And so this is the last time that I'm going to give you these formulas. You can put these in your file, you can put them wherever you want to put them, but it's up to you now to start to remember this stuff, because these are tools that you're just going to be expected to have for the rest of your math education. So we do not know how to find the antiderivatives of that. That's just way too complicated. So what we're going to do is we're going to use trigonometric identities. 1 is equal to sine squared x plus cosine squared x. So all I did was just replace the 1 with sine squared x plus cosine squared x. But of course you can see what's going to happen. These cosine squared x's are going to cancel out, and you're going to be left with cosine x over sine squared x. Now it doesn't appear that we've really accomplished anything, but if we can do some tricky algebra, we can take sine squared x and break it into 2 sine x's, and we can actually factor out one of the sine x's. We can factor out 1 over sine x, that is, to be clear. Now, if you don't know how it is you can do that, well, you're multiplying 2 fractions. And whenever you multiply fractions, of course, you know that you just multiply the numerators, and then you multiply the denominators. And so that these are just things that you're going to have to be comfortable with. So 1 over sine, that's the reciprocal identity. That just becomes cosecant x. And this is a ratio identity. That's just cotangent x. Again, these are all things that you're going to be just expected to know. And calculus students will typically say, like I said, they'll say, this is not fair. How am I supposed to remember all this? Well, again, you didn't learn all that stuff in previous courses for no reason. You learned it because you're expected to know it at this point. Now, the derivative of cosecant x is negative cosecant x cotangent x. So we almost have that expression, but there's no negative there. So all we have to do is write negative cosecant x. So now when we find the derivative of this, we're using the constant multiple rule. So the derivative of this is the constant -1 times whatever the derivative of that is. But the derivative of that is this expression up here. So you have a double negative, the negatives go away, and you end up with what we're looking for, which is cosecant x, cotangent x. So we just had to do a slight modification there at the end. So are you required to know these trigonometric identities? Absolutely. You're required to just be able to pull those out of your bag of tricks whenever you're required to. So I'm just warning you, I'm letting you know that those trigonometric identities, they're coming for you. You have to know them. So now we have a double angle sine of 2x. A lot of students would try to divide these. You can't divide them because this is something totally different from that. But we can change sine 2x to 2 times sine x times cosine x. That's a double angle identity. We learned that in my trigonometry course. Now again, if you don't remember that, that's not uncommon. Most students don't remember it. But if you expect your calculus teacher to show you that, or to find those formulas for you every time that you need to use that, again, it's not going to happen. You're going to be expected to know those formulas at this point in your math education. So now, the antiderivative is pretty easy. It's just 2 times sine x, because the derivative of sine x is cosine x. Alright, so there's another example. Here's an example where we have sine squared plus cosine squared. We certainly can't find the antiderivatives of this. It's too complicated, but we can change sine squared plus cosine squared into 1. We already did that once in a previous problem. And then 1 over cosine squared, well, that's the same thing as 1 over cosine x times cosine x. Then we can factor it to get 1 over cosine x times 1 over cosine x. And I want to be clear that I'm going slow here. You don't have to show every single one of these steps. You can jump forward. But now we're going to use the reciprocal identities. So each one of these is equal to a secant x. I'm sure you probably remember that. And then we have the integral of secant squared x dx. Now, the derivative, I'm sure you probably remember, or at least it seems kind of familiar to you, the derivative of tangent x is secant squared x. So what is the antiderivative, or the family of antiderivatives? That's just going to be tangent x plus c. That's it. All right. So again, we're just using trigonometric identities. Trigonometric identities are all over the place in the calculus curriculum, so that's why I'm kind of harping on this idea. Now, this is a challenge problem. Again, you can't just throw in a function here and expect us to be able to find the antiderivative functions. We don't know the antiderivative functions of every function that you can just throw in an indefinite integral. So a lot of students will look at this and say, well, we can't do that. But actually, it's a trick. We're going to change tangent x to sine x over cosine x. And the reason that that's going to be useful is we're going to use the last differentiation formula that we learned, number 13. This is why this is a challenge problem, is because we don't, at least in this curriculum, we haven't used this very often. But remember, if you have a natural log function, the derivative of that is the derivative of whatever's inside the function divided by whatever's inside the function. I know that's very strange, but that's how that works. And the reason that that works here is because the derivative of cosine is equal to sine x. So, or excuse me, the derivative of cosine is equal to negative sine x, but we still have what we need to do this. So it's going to be natural log cosine x. And of course we need to add the c value. Should probably put that in parentheses just to be clear. So let's find the derivative of this and see if we did it correctly. So the derivative of this is the derivative of whatever is inside the natural log function divided by whatever's inside the natural log function. That's how you find the derivative of natural log. So what we get is negative sine x over cosine x. Well, that's not quite what we want. We want an expression that doesn't have a negative. So how do you modify that? Well, we just put a negative in front of the natural log. Okay, so remember, if you want to find the derivative of an expression that is a constant times a function, the derivative of that is just the constant times whatever the derivative of this is, and that is going to be that, but the negatives cancel out, and you're left with sine x over cosine x. So that is the antiderivative. That was kind of a challenge problem, again, mostly just because it's tricky. We have to use a ratio identity, and we also have to remember differentiation formula number 3, or excuse me, number 13. Okay, so I want you to take a picture of this problem here. This is going to help you with the problem that you're about to do. And I also want you to get a picture of these problems, or I can just leave those in the window for you if you want. But I want you to try number 23. And be aware you're going to have to use a Pythagorean identity. When you come back, we'll do it together. Okay, we're back. So you can verify that by finding the derivative using your derivative formula. So now I want you to try this problem. Now this problem is going to be a little bit more difficult because there's actually 3 different double angle formulas for cosine 2x. And if I remember correctly, I think 2 out of the 3 are not going to work, but one of them should work. And the one that is going to work should be 2 cosine squared x minus 1. If you use 1 minus 2 sine squared x, I don't think that's going to work without having to do extra steps. And same thing with cosine squared x minus sine squared x. That's not going to work either without having to do extra steps. So you want to use 2 cosine squared x minus 1. Try number 24. When you come back, we'll do it together. Okay, we're back. So again, you always want to confirm, find the derivative of that, and then see if you get the original expression. So if you got that right, excellent. Okay, so now we're going to need another Pythagorean identity, as we did up here. See what you can do. Remember, there's 3 Pythagorean identities. So which one is this? Now you can change the numerator, or you can change the denominator. It doesn't really matter. You're going to get the same answer. So try number 25. Do your best. If you get stuck, that's okay, but try 25. When you come back, we'll do it together. Okay, we're back. Because remember, the derivative of x is 1, right? So if you got stuck there, that's okay, but now you know that that's just going to be x plus c. So we have one more problem here. This is a challenge problem. You're going to need to use a ratio identity. That's one of your trigonometric identities. You're also going to need to use formula number 13. So in case you don't have that right in front of you, this is formula number 13 up here. And if you don't have the ratio identity, remember I gave you that sheet that shows you all the trigonometric identities. You need to have that identity memorized. At the absolute least, at the very, 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 very least, you need the reciprocal identities memorized, the Pythagorean identities, and the ratio identities. If you don't have those memorized, then you don't have your head in the right place when it comes to the math curriculum. So you need to have those memorized at this point. So go ahead and try number 26, and when you come back, we'll do it together. Okay, we're back. So again, use differentiation formula number 13 to find the derivative of this, and you see that the derivative of sine is cosine, and then you divide that by whatever's inside the log function, which is sine. So there you go. So that was kind of a challenge problem. Okay, so at this point, we're going to learn the fundamental theorem of calculus. A couple classes ago, we discussed that the two branches of calculus, differential calculus and integral calculus, have what we call an inverse relationship. They are inverse operations of each other. Integral calculus is when you try to find the area under a curve. Differential calculus is when you try to find the slope of a line that's tangent to the graph of a function, or the slope of a line that's tangent to a curve. So to find the slope of a line tangent to a curve, you need the derivative, right? Well, it turns out that when you do the opposite operation, which is antiderivative, well, guess what that helps you to find? It helps you to find the area under the graph of a function. That's how differential calculus and integral calculus are related in an inverse relationship. So we're going to learn how to use that principle to find the area under a graph, specifically the area between the x-axis and the graph of a function. And we're talking about the exact area, not just an approximation, the exact area. Now, in previous classes, we used the hard way. This is when we calculated the area of this shaded region the hard way, using the hard way. This is the difficult way, and look at all the things that we had to do. We took up an entire page just doing all this math, and we used, of course, this formula here. You probably remember that formula. And we were able to find the exact area by evaluating the limit as the number of rectangles approach infinity. But as you can see, this is really complicated, and this method doesn't really work for a lot of functions. And even if we have just polynomial functions, we have to have a lot of complex formulas to be able to use this method to find the area under the graphs of polynomial functions. It's just tedious. So now we're going to learn the fundamental theorem of calculus and how it's used to find the exact area. So we're going to find the area under the curve, just like we did in this problem in previous classes. Notice we have the same graph. We're looking for the same area here. But now we're going to use the fundamental theorem of calculus. Okay, so this is the easier method. So what we're going to do is we're going to look at this function over here, and instead of finding the derivative, that's what we would do if we wanted to find the slope of a line that's tangent to the graph like this. Instead of finding the derivative, we're going to find the antiderivative. So we're going to write capital F of x, because remember, capital F is usually used to notate the antiderivative. If we've got lowercase f, then capital F is the antiderivative. And that, of course, is 1/3 x to the third power plus 2x plus c. So we've done that quite a bit. We know how to do that. And so here's how we use the fundamental theorem of calculus to find the exact area. We're going to find the exact area that you see here, this shaded region here. And here's what we do. We take our antiderivative function and we plug in 2. I got 2 from here. That's our right bound or limit. Sometimes they call these the limits. And then we're going to subtract our antiderivative with 1/2 plugged in. That's the number down here. That's where we got that. And that's it. It's as simple as that. So Isaac Newton was able to prove that this works back in the 1600s, and that's why he's considered to be one of the greatest mathematicians, because he actually demonstrated this with a proof that this actually works pretty much in every single case, as long as the graph is continuous. Now, if you have breaks in the graph, this will not necessarily work. But if the graph is continuous, then you can use this method. So let's actually employ this method. So we're going to take this function and plug in 2. So we have 1/3, 2 to the third power, plus 2 times 2 plus c. So I just calculated this here. All right, then we're going to subtract the same function, our antiderivative function, but instead we're going to plug in 1/2. And let's move it over a little bit. And you have to be really careful. Notice that I'm using parentheses. Those, let me show you. I'm going to color those pink just so you can see those. They stand out. You see those pink parentheses? I'm going to tell you something. If you don't write those parentheses, you're going to have a big problem. We're subtracting all of that. Okay, you need to understand that we're subtracting all of that. It's very, very common for students to have sign issues with this, so be careful. So now we have 1/3. I'm going to go very slow here, just so you can be absolutely sure what we're doing. But I don't really need to go slow. I mean, this is just basic math. So I'm just doing my calculations. And then we get 8/3 plus 4 plus c. And then when you multiply these, we get 1/24. But now I'm going to distribute the negative into each one of these terms. And there you go. So we just have to simplify. And so the 4 and the 1 can be combined. So we obviously get 3. And if I multiply both sides of this fraction by 8, I get 64/24. And I can combine those. 64 over 24 minus 1 over 24 is 63 over 24. And I also want you to know that the c's, well, they just cancel out. C minus C is 0. Alright? So I'm going very slow here. You don't have to go this slow. You can just calculate the numbers as quickly as you want to calculate them. So 24 goes in twice, and it looks like we have a remainder of 15. And that's going to give us 5 and 15 24ths. And that's 5 and 5 eighths. So that is the fundamental theorem of calculus. We found the exact area of the shaded region. Now, you might look at this and you might say, well, we still had to do a lot of work. Well, I'm going slow. If you want to go quickly, you can do this, you know, probably with 2 or 3 steps. It doesn't really take that much time. And we're going to show you some notation that we're going to use to make this even easier to write. We're also going to show you the notation that is used to actually indicate this area, which we have not gone over yet, but for now we're just learning the concepts. So you can see here that this was the easy way, or the easier way. This is the hard way to find the area. So this is what people would do to find the area, and then Isaac Newton came along and said, well, you can use this method, which is a lot easier. The big question is, did we get the same answer? So over here we got 5 and 5 eighths. Over here we got 45 over 8. Is that the same thing? And the answer is yes. If you change this to an improper fraction, you get 45 over 8. And you can confirm that on your calculator if you want to. So that is the fundamental theorem of calculus. So it's kind of a fascinating thing that 2 problems that don't seem to be really related at all are actually related. And they're problems that both deal with limits, because when we do integral calculus, we have limits. When we define the derivative, we have limits. Remember, the definition of the derivative is the limit of f of x plus h minus f of x over h as h approaches 0. So we have limits involved with this stuff, and Isaac Newton discovered that these 2 problems can be used together, so to speak, in concert to solve 2 different problems. So let's try another one of these problems. So we're going to find that shaded area. F of x is cosine x. The first thing that we need to do is find the antiderivative function. So that's obviously going to be sine x. We know the derivative of sine x is a cosine x. Now, notice in the previous problem that c canceled out. The orange c values, they canceled out. Well, as you might imagine, that's always going to happen. C is always going to cancel out. So when you start to get used to this process, you're not going to write C anymore. You're just not going to do that. It's not necessary. You can just skip writing C. But for now, I want you to see why we don't have to write C. So I'm going to just keep writing C. And I want you to see how the C value always cancels out. And it's important to understand that when we find the exact area, the function that we use here and the function that we use here, they're the same function. So again, the fundamental theorem of calculus tells us that if we want to find the exact area under this the graph of this function, we simply find the antiderivative of the function, plug in our right bound, and then subtract the antiderivative of the function with the left bound plugged in. Okay? And because these two functions are assumed to be exactly the same function, you're just taking an antiderivative function and you're using it for both of these. What that means is that the c value has to be the same for both of these. Okay, c can be anything. But if you're using this function here and you're also using the same function here, well, obviously the c values are going to cancel out. So they always cancel out. So I'm going to plug in 0 to our antiderivative function. And I'm going to subtract the antiderivative function with negative 1/3 plugged in. And we just have to calculate and we'll have our answer. So sine 0 is actually 0. Now this is where you need to go to your trigonometric, your knowledge of trigonometric functions and whatnot. Remember, if you want to find the value of a trig function when you're plugging in a quadrantal angle, you have to use these types of graphs. 0 is 0. Pi over 2 is 1. Pi is 0. 3 pi over 2 is negative 1. 2 pi is 0. You need to know that. You're going to be expected to just know that on your own. So use that information on your trig cheat sheet, so to speak, and you'll have your answer. So sine 0 is just 0. Now, what is sine negative pi over 3? Well, that takes a little bit more work. You have to go to your knowledge of sine functions. And by the way, most calculus teachers, they're not going to show you this. They're just going to say, if you don't know this, then tough. Because you're expected to know this by the time you reach calculus. And if you don't, your calculus teachers aren't going to care. So I know that's pretty harsh, but that's honestly the way it is in calculus courses. Your calculus teacher expects you to know these things. So we have negative pi over 3. For positive angles, we rotate counterclockwise. For negative angles, we rotate clockwise. And so we get something like this. And so negative pi over 3 is 60 degrees. So this angle must be 30 based on the triangle sum theorem. And remember, the angle opposite 30 is always x, and the angle opposite 60 is always x root 3, and the hypotenuse is always 2x. Now, why is this negative? Well, because the triangle is going down. This side's going down. So sine is the side opposite divided by the hypotenuse. Now, again, what I just showed you right there, what I just showed you is something that your teachers are not going to show you. So I'm trying to be thorough here, but just be aware that, I don't mean to sound like a broken record, but you're going to be expected to know how to do that on your own. Okay, so the c's cancel out. Remember, they canceled out in the previous problem. They're going to always cancel out. And we're going to learn a method to where you don't even have to think about the c's. So now the question is, what is sine of negative pi over 3? Well, we just calculated that. It's the opposite side from the angle divided by the hypotenuse. So negative root 3 over 2. That's a double negative, so we get root 3 over 2. That's the answer. Okay, so again, this is the fundamental theorem of calculus. Let's try another problem. We're going to find the area under that curve, specifically the area between the x-axis and the graph, using the fundamental theorem of calculus. So we have this function here. In order to use the fundamental theorem of calculus, we have to find the antiderivative function, or the family of antiderivative functions. Now, this is a little tricky. Remember, the derivative of 2x is 2x natural log 2. So if we want to find the antiderivative of that, we need to do the opposite of multiplying by natural log 2. We're going to divide by natural log 2. So you can write that as 2 to the x over natural log 2. It's the same thing, but it's easier for students to think of it as a multiplier. And of course, before we forget, we need to add our c value. Okay, so in order to confirm that this is the antiderivative functions, just find the derivative. When you find the derivative of this, remember the constant multiple rule says that when you're finding the derivative of a constant times a function, the derivative is the constant times the derivative of that function, and the derivative of the yellow function is 2 to the x times natural log 2. So these will cancel out, and you're left with 2x. Okay, so now we're going to use the fundamental theorem of calculus. We're going to find the exact area, which is the antiderivative function with 2 plugged in. I got that from here. Minus the antiderivative with 1 plugged in. -1, which I got from there. Okay, so the antiderivative function is 1 over natural log 2 times 2 to the 2 power minus 1 over natural log 2 2 to the -1 power. And whoops, I forgot to write my c's. You don't really need to write the c's because they cancel out, but for now I just want you to see how they cancel out. So I'm going to keep writing those. And it's so important to put these parentheses. Do not forget to write those parentheses. So let's double check everything and make sure we did everything correctly. Everything looks correct. So now we just have to simplify. So we get 1 over natural log 2 times 4 plus c minus 1 over natural log 2 times 1 over 2 to the 1 power. And we can write that as 4 over natural log 2. The c's obviously cancel out, and we're left with 4 over natural log 2 minus 1 over 2 times natural log 2. And we can get a common denominator by multiplying both sides of this fraction by 2, and we get 8 over 2 natural log 2. And 8 minus 1 is 7, so we have 7 over 2 natural log 2. And that's the answer. That's the exact area of this region here. Now, we can change this to a decimal if you want, but why do that when we have the exact answer? I mean, this is the exact area. We don't want to have to round off if we don't have to. So, that is the fundamental theorem of calculus. So I want you to get a picture of this information here. We have not stated the actual theorem formally yet, but we're going to get to that. For now, I just want you to learn how to use the theorem. So I want you to try example number 4, but get a picture of these also. Try example number 4. So the first thing that you're going to do, and again, what we're trying to accomplish here is we're trying to find the area of the shaded region. So the first thing you need to do is find the antiderivative function. What is that? Then, to find the exact area, you simply plug in the right bound, and then plug in the left bound, and then you subtract them. So go ahead and try example 4, and when you come back, we'll do it together. Okay, we're back. So we get 4. So is that the correct answer? Well, we actually did this exact same problem in a previous class, and yes, it should be exactly 4. So if you got that right, excellent. Isn't it interesting that the area here is exactly 4? So you can use example 4 to help you. Try example 5. Remember, the first thing to do is to find the antiderivative of this function. And then use your fundamental theorem of calculus. So try example 5. And for example 5, obviously before we find the antiderivative, we need to change the form of this expression. So that's step 1, is find the antiderivative function of f. But before you can do that, we need to change root x to an expression that has an exponent. So try example 5. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. You can write that as 4 2/3 if you want. But you can also leave it as 14/3. So notice that these c's just keep canceling out over and over and over again. So it shouldn't be a surprise to you that we're going to get to the point where we're not going to even write those c's anymore. It's just a waste of time. But for now, I'd kind of like you to just keep writing the c's, just so you can understand why they cancel out. So get a picture of these two problems that you just did, and they can help you with example number 6. So try example 6. Remember, we have to start by finding the antiderivative of this function here, and then use the fundamental theorem of calculus. Try number 6. When you come back, we'll do it together. Okay, we're back. Pi over 4, that would give us a triangle like this. That's 45 degrees is pi over 4. And so that's a 45, 45, 90 degree triangle. So these sides, whatever they are, the hypotenuse has to be that length times root 2. So cosine is the adjacent side of the reference angle divided by the hypotenuse. So that would be 1 over root 2. So if you got that answer, excellent. Now, a lot of students would say, well, you have to rationalize the denominator. If you want to do that, that's okay. But again, in calculus, most of the time, calculus teachers don't really care about that. But you do need to know that these two expressions are the same. And if you don't know that, then you're going to be in big trouble when you go into upper math, because you're going to see those expressions changed back and forth between those terms quite a bit, or those forms. So if you got that one right, excellent. So now we're going to learn the notation that is used with the math that we just learned. Now, we learned about indefinite integrals in the previous class, and we reviewed them today. An indefinite integral, like this, for example, that gives you a family of functions. And so this is what we call indefinite, because we don't know what c is, and in fact, we're not necessarily even plugging in a number for x. So we have an expression with unknown values, an unknown here and an unknown here. We don't know exactly what the constant would be or the variable, so that's why we call this an indefinite integral. Now we're going to learn what's called a definite integral. A definite integral, by definition, and when you say by definition, that just means mathematicians just decided that this is the way it's going to be. It's like when a person has a baby, they name the baby. They just say, I decide this baby is going to be George or Bill or Pete. You just decide that that's going to be the name. Well, mathematicians have decided by definition that this expression here is the area between the graph of f of x and the x-axis from x equals a to x equals b. So that area that we've been trying to find as we started learning integral calculus, that area is just defined to be, or this expression here is defined to be the area. Okay, so if f of x is this red graph here, this expression is the area. And notice that there's only one difference. Look at this blue expression, which is the definite integral, and look at this green expression, which is an indefinite integral. There's only one difference. The difference is the definite integral has a and b, but the indefinite does not. Because the definite integral, the blue expression, is just a number. The indefinite integral, like I said, is an expression with all kinds of unknowns. It's indefinite. But the definite integral is just an area. It's a number. Okay, so that's why they call it definite, is because it's a definite number. So this is the notation that we're going to use for now on to indicate the area under the graph of f of x, specifically the area between f of x and the x-axis from x equals a to x equals b. So here's the fundamental theorem of calculus stated in a formal way. We have this expression we just learned. What is that? What is this expression? This is the area between the x-axis and the graph of f of x between these two x values. That's the area. That's the notation we're going to use for the area under a curve from now on. The fundamental theorem of calculus tells us that the area between the graph and the x-axis between x equals a and x equals b is the antiderivative of this function with b plugged in minus the antiderivative of the function with a plugged in. So that's it. That's the fundamental theorem of calculus. So we just used this a bunch of times. We just didn't have this special notation that we're going to learn to notate it. Now, be aware that this theorem, it only works if the function is continuous on the integral. So if you're finding the area from a to b, but you have a discontinuity in the graph, let's say that you have like an infinite discontinuity, well, it's not going to work because the area is not really defined as you go up into infinity, right? If you have a break in the curve like this, and all of a sudden it just breaks, well, the fundamental theorem may not work in that case. So you have to have a continuous graph. So you might want to get a picture of all this information here. Now, because this is such an interesting theorem, some students may wonder what the proof is. Remember, postulates don't require proofs. We just accept them to be true. But theorems require an explanation. You have to actually show that the theorem is true with some sort of argument. But we don't usually show proofs in math courses because students will just fall asleep. And the reason that they'll fall asleep is it's kind of like showing somebody how to dismantle a car engine if you're trying to teach them how to drive the car. Well,
of course, if you're trying to learn how to drive a car and somebody's teaching you how to dismantle the engine, you're probably going to fall asleep. You're probably going to not really be very interested in that unless you want to be a mechanic. If you want to be a professional mathematician, then proofs are important. And you have to understand that proofs are things that you have to think about. They're not things where you can just show a person and then they'll say, of course, I've got it. That makes perfect sense. It doesn't work that way with proofs. Each step in a proof is something that you have to think about for minutes, hours, days, or sometimes even weeks. Some mathematical proofs take hundreds of years of thinking about to actually figure out. So for these reasons, proofs are not really covered a lot in the math curriculum. But again, because this theorem is so interesting, I'm going to show you a proof in the next video, but I'm not going to require you to watch that video if you don't want to. So it's not going to be a required video in this course. And the video may only be maybe 10, 15, 20 minutes long. But if you want to see the proof, you can watch that video. If you don't want to see it, if you don't care, then you don't have to watch it. But we have learned this new notation for the area between the x-axis and the graph of a function. And now we're going to use that notation.
So we're going to do the exact same thing we did before, no difference whatsoever, except we're going to use our special notation. It says find the value of each integral below. Graphs are presented for context. So you don't really need the graph to find the value of this integral, but I just want you to see what we're finding. We're finding this yellow area here. So we have this function graphed, and we're finding the area between -1/2 and 1. You see that down there? So you're going to see an expression like this, and you're just going to be expected to know how to find the answer. Now, sometimes you don't have to use the fundamental theorem of calculus. Sometimes you can just see what the area is. You can just, if you had a graph that was linear, well, you could just use rectangles. If you wanted to find the area between here and here, you could just break this into a triangle and a rectangle and find the area that way. You wouldn't need the fundamental theorem of calculus. Okay, but when you have this function, well, that's a curve. We need the fundamental theorem of calculus in order to do that. So that expression is going to be, I guess we'll just write it up here, that's equal to the antiderivative with 1 plugged in minus the antiderivative with -1/2 plugged in. So I got the 1 from there, and I got the -1/2 from there. So that's very important to understand. I guess I'll just leave those there so you can understand where these numbers are coming from. Okay, so the first thing we need to do is find the antiderivative function, and that's going to be looks like 1/2 x to the 4th plus 5/3 x cubed plus 1/2 x squared plus 4x plus c. Now, remember the c values, they always cancel out. So, first of all, let's check this. Let's find the derivative of this and see if we get the original function. So it looks like we do, but I accidentally put a plus sign there. See, that's why you have to double check. Constantly go back and double check, double check, double check, double check. Okay, so this c value always cancels out, so we really don't want to write it over and over again. It's just not necessary. So the way that we write this is, let me rewrite the integral down here. We write the antiderivative and we're doing the same thing that we did in the previous problems. There's no difference whatsoever. Except because we know that that c value is going to cancel out, we just don't write it at all. And we write a bracket here, and I write -1/2 at the bottom and 2 at the top. This here, that's the same thing as this. But this is just like a faster way to write what we're doing. Now, sometimes you write a bracket over here if you have to multiply it by something, but you don't have to write that bracket unless you're multiplying this entire thing by something. But for this problem, I'm just going to write the plus c because I don't want to confuse things at this point. But in the next problem, I'll show you how to use that that notation, because you're going to use it for now on. So we don't have a lot of room here, so I'm going to have to write this down here. And of course I'm going to have to replace the x's with ones. So we have the antiderivative is 1/2 times 1 to the 4th power minus 5/3 times 1 to the 3rd power plus 1/2 times 1 squared plus 4 times 1 plus c. And then we have to subtract the antiderivative with -1/2 plugged in. So 1/2 -1/2 cubed, or to the 4th power actually. And as you can see, don't really have a lot of room here, so I'm going to go down one more line. And we have minus 5/3 -1/2 to the 3rd power plus 1/2 times -1/2 to the 2nd power plus 4 times -1/2 plus c. And I'm going to write my parentheses with a bright color so you know that we have that there, because if you forget those pink parentheses, then man, you're going to have a hard time with this. So we found the antiderivative and we plugged in 1, and then we found that we used the antiderivative and we plugged in -1/2 and we're subtracting. So we're just using the fundamental theorem of calculus just like we did in the previous problems. So now we need to go back and check, because there's a lot going on here. We don't want to waste our time unless we are doing this correctly. So let's make sure we're doing everything correctly. I'm checking all my work and going over this very meticulously, and it looks like everything is correct. So now you can jump through this as fast as you want to. And 1 cubed is 1. 1 squared is 1. 4 times 1 is 4. -1/2 to the 4th power is +1/16. And -1/2 to the 3rd power is -1/8. 1/8. and negative 1/2 to the second power is 1/4. And 4 times negative 1/2 is negative 2. Okay, so let's go back and check everything, make sure we did everything correctly. Everything looks correct as far as I can see. It's a lot of calculations, so you got to be careful. And I'm going to make these parentheses a bright color just so we know to watch out for those. So then we have 1/2 minus 5/3 plus 1/2 plus 4 plus c. And I'm going to go ahead and distribute. So we have minus 1/32. Actually, before we distribute, I'm going to go ahead and simplify a little more. And positive 5/24. And so on and so forth. So we have not distributed the yellow negative symbol yet. I'm going to add some of these numbers. 1/2 plus 1/2 is 1, plus 4 is 5. And then I'm going to distribute the negative finally. And you can see, as usual, the C's are going to cancel out. Again, notice that the C's always cancel out. That's going to be important to understand later. So now we have 2 plus 5 is 7. And I'm going to combine these fractions. And we get, looks like negative 45 over 24. So I combine those numbers, and I combined these numbers, and I'm going to combine these remaining fractions, and we get negative 5/32, it looks like. And so I think we can reduce this fraction, so that's good. Divide both sides by 3 and we get 15/8. And multiply both sides by 4 and we get 60/32. And we're out of room, but that's okay. So we have 7 minus 65/32, whatever that ends up being. And 65/32, that's 2 and 1/32. And so it looks like we're going to end up with 4 and 31/32. So that is the answer. So sorry that problem was kind of long, but that's our new notation we're going to use. And let's try another problem. Here again, we're supposed to find the value of this integral. And that's just the area. But we learned from the fundamental theorem of calculus that you just find the antiderivative, and then you plug in the right bound and subtract the antiderivative with the left bound plugged in, and that's it. So it's that simple. It's that simple. So first, let's find the antiderivative function. So that's going to be negative 3 cosine x plus 0.4 x squared plus c. So you can verify that. Now I'm going to show you the special notation that we use really for the rest of the calculus curriculum to use the fundamental theorem of calculus. So now we're going to start using it. So what we do is we write the antiderivative function, this function up here, but we don't write c. We just leave that off. And we write 1 to 4 with a bracket. And what that tells us to do, and again, we don't write c because the c just always cancels out. Why write it over and over again if it just keeps canceling out? We don't really need to write that. So we have this part of the antiderivative function, and we're going from 1 to 4, and then we just plug in the numbers. So that is the way that we typically show that we're using the fundamental theorem of calculus. So we plug in 4, and then we subtract, but you have to be careful. Use those parentheses. That's where students really go wrong with this stuff. You have to be very, very careful. So let's move this over a little bit so we have some room. So I'm going to write the antiderivative function again, but this time I'm going to plug in 1. I got that from there. And that's it. So let's go back and make sure we did this correctly. And it looks like we did. So again, this is just the fundamental theorem of calculus. Same thing we've been doing. It's capital F of 4 minus capital F of 1. That's all that is. But this is just a way to kind of abbreviate what we're doing. So now we have negative 3 cosine 4 plus 0.4 times 16. And then I'm going to go ahead and distribute the negative, so we have plus 3 cosine 1 minus 0.4 times 1. 1 squared is 1. And 0.4 times 16 is 6.4. And please make sure that your calculator is in radian mode. If you're using a TI-84 Plus, go to the mode button at the upper left, middle upper left, and go down and make sure that radian is highlighted. Push the blue second button and then the mode button again to quit out of that. So we can go ahead and combine the 6.4 and the negative 0.4, and we just get 6. And so we just need to calculate this, and we can't do this without the calculator. So don't be afraid to use your calculator. So when we calculate all this, we get 9.58 approximately. 9.5818, I'll say. So again, we're just using the fundamental theorem, but this is called a definite integral because it just gives us an exact number. It's not giving us a function. This will be considered the result of an indefinite integral because it's a function. It's got variables, we got unknown constants. But the definite integral, which is what we found, that's just a number. It's an area. It's this shaded region here. And we use the fundamental theorem of calculus, you see here, and we use this special notation, and we dropped the constant. At this point, you can drop the constant if you don't want to use that. Okay, so let's try another one. So first we're going to find the antiderivative. You may recall that the derivative of natural log x is 1 over x. We just need the negative in front. So that's the antiderivative. And so I'm going to copy this. We don't really need to copy it. But I wrote the antiderivative there, so I don't want to erase that. So we have negative natural log x, but we're not going to write the c value. We're just going to write brackets and then write a -3 and a -2. And what that means is that we're plugging in -2 using the fundamental theorem of calculus and then subtracting the same expression with -3 plugged in. Now, unfortunately, at this point, we have an issue. The issue is we're not allowed to have negatives inside our natural logarithms. We can't do that. So, that means that we can't do this. We can't use the fundamental theorem of calculus to find the area that we're looking for here, because we can't have a negative inside a logarithm. But it turns out that we actually can. It turns out that if you just pretend that those numbers are positive, just change them to positives. See how I changed my my numbers to positives, then the difference that you get here is the exact area that we're looking for. Now, you're going to say to yourself, wait a second, we can't just change the sign of a number just because we feel like it. And that's correct. We can't just change the sign of a number. But in this case, it actually works. It just works. There's no logic behind it other than the fact that it just works. So oftentimes what you're going to see is absolute value symbols whenever you see an antiderivative of a function like this. You're going to see absolute value symbols like this, because it turns out that you can find the area, you just have to change the numbers to positive numbers. So what is the meaning behind that? Why is that? That's kind of a mystery. Well, you don't have to understand why that works. You just have to know that in this case it does work. So we just have to find negative natural log 2 plus natural log 3. If you ask teachers or textbook writers why this works, they won't give you an answer, because they'll just say, well, it just works, and it does. And if you want to study, the logic behind, why this works, then you can do that. But that's kind of an offshoot from this course. Just be aware that when you find the antiderivative of an expression like this, oftentimes you're going to see absolute value symbols written for practical reasons. So at this point, we need our calculator. We could just write natural log 3 minus natural log 2. In fact, we could combine that into one expression. Natural log 3 minus natural log 2. Remember our logarithm properties. This is another thing that you're just going to be expected to know. I'm going to write it log base base b of, well, I guess I'll use log base x of a minus log base x of b is equal to log base x of a over b. Do you recall that? If you forgot, that's okay, because every student forgets. But this is something we learned in my intermediate algebra course. So we can actually combine this into natural log 3 over 2, and that's the exact answer. Now, if you want to put it in decimal form, you can do that, but this is better because it's an exact answer. So in this problem, we had a lot of weird things going on, but in calculus, a lot of weird things do happen. So you just gotta get used to it. So I want you to take a picture of all this information here, and I want you to get a picture of these 3 problems that we did. And I know what you're asking yourself. You're asking, should I write C when I find the antiderivative, or should I use this method where I don't write C? And the answer is, whatever you're comfortable with. Eventually, you're going to do it this way. So, you're going to get on board with that pretty soon, eventually. But if you're not quite sure how this notation works, you're kind of having some trouble with that, you can always go back and and write your C's just so you can understand how the fundamental theorem of calculus is done. So now I want you to try number 30. So we're finding the area of this shaded region. Try number 30. When you come back, we'll do it together. All right, we're back. So there you go. If you want to, you can write 2 1/3. I don't really care. Most calculus teachers don't care. So if you got that right, excellent. So I want you to try number 31. And when you come back, we'll do it together. All right, we're back. 1.88962. So if you got that answer, excellent. So you can look over that if you want. We just have one more quick problem. So I'm going to leave this in the window, and hopefully you can see this problem. It's kind of hard to see, but try number 32. When you come back, we'll do it together. Okay. And e to the 0 power is 1. So you can just leave your answer like that. That's probably fine. So that is the exact area that you see here. So we learned definite integrals. A definite integral is an integral that gives you an exact number. We learned the fundamental theorem of calculus, which is how you find definite integrals in most cases. And it's the fast way to find areas under curves. We learned the special notation for definite integrals, and we learned this special notation to make the work go a little faster. So if you got that right, excellent. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And number 2. And number 3. And number 4. And number 5. And number 6. And number 7. 8. And number 9. But don't go before you get your homework. Remember, the homework is not optional. It must be done completely and correctly. So here's the first page of the homework. And some of these problems are kind of small, so I'm going to give you a chance to take closer pictures if you want. You may not need to, but here's screenshot number 2 of the homework. And zooming in on each one of these problems. And here's screenshot number 3. And here's the answers. So make sure you check all your answers. If you get the wrong answer, then that means you need to go back and fix what you did wrong. The homework must be done completely and correctly. So get that homework done, and I'll look forward to seeing you in the next class.